Good afternoon, everyone. My name is Ryan Darcy, and I'm the Teacher Development Manager for Macmillan Education International Curriculum and Caribbean. Thank you so much for joining our webinar this evening in the UK with Debbie Roberts, who is going to be focusing on planning primary science lessons, focusing on inquiry-based skills. If you have any questions, feel free to write them in the chat box and we'll do our best to answer your questions. So I will pass it over to Debbie now. Thank you.
Hi everyone, good afternoon. I hope you're all well. Welcome to this wonderful session on planning primary science lessons. If you have any questions or any comments or anything, please feel free to write them in the chat box. And if you see me going like that, it's because I'm actually reading them as I deliver this webinar, because I do like it to be interactive and I like to know that you are getting information from this, and if you've got any questions, I'd love to try to answer them. So let's get going. So welcome, and the objectives for this session are mainly to plan engaging and motivating lessons for our students, to become more confident in allowing students to take control of their learning, to actually not be too teacher-led and to be more student-led. I often ask or present a challenge to people, to teachers, and I say, find me a nice picture. Do a Google search, do an online search and find a nice picture of students learning in a primary classroom. And they go, oh yeah, that's easy. And I say, yeah, but try to get one without a teacher on it. And I'll set you that little challenge. There you are, there's your homework. Try to find a picture of a lesson in a primary science classroom where you can't find the teacher. And you won't find one, because the teacher is always there leading the learning. And we need to become more confident and let go of that little grasp and let the students take control of their learning, so that learning is done with them as a team and not to them as almost a victim. We also want to encourage the development of skills, because, as I always say, and I'll continue to say, we have no idea what the content will be of a person's job in 10, 15 years' time. We don't know. We have no concept of it. Technology is working at an incredible pace, and we don't know how technology will develop over the next few years. And so we can't really just lean on the content and students knowing the content in a particular subject area. We need to make sure that they have the skills to be able to develop and adapt and comply with new technology and new working environments. I mean, look at us. Who would have thought? Who would have thought 2 years ago, 3 years ago, when I was in Jamaica, who would have thought that we would be doing lots and lots and lots of online support like this, because we wouldn't be able to be there. And it's not the same as being there. It's not the same as sharing your fantastic good practice, your ideas and your experience. It's not the same. But this is better than nothing. And at least we're together, and at least you know that you've got the support, and we're here and we're still that team that we were before. It's just slightly different. So who knows if it's changed this much in 2 years? Who knows what it'll be like in 10 or 15 years? I wonder if I'll still be working. Anyway, if we were together, I would say to you now, so what do you think makes a good science lesson? So, as a teacher, your opinion on a good science lesson would probably be slightly different to that of a parent. Even though some of us are parents and teachers at the same time, our expectations are different depending on the role that we're in. I always say to people, lots of parents and teachers, they come to me for advice and say, you know, we're working from home. I'm trying to teach my children from home, and I'm also teaching from home. I've just been talking to my son now, who's a secondary computer science teacher, and he's just said to me, Mum, I'm exhausted. This is really hard work. This is really tiring, because he's delivering lessons online all day from home, and it's different. It's very, very different. And I say to parents when they come to me and say, but I'm a teacher, I should be able to teach my children from home. And I say, yeah, but you're not your child's teacher. You're your child's parent. And it's difficult sometimes to blend the two, and it's impossible because students see us as weird old parents and never anything else. But my point is that we would view a lesson in different ways depending on what role we're playing. Even the assessor, we might think that was a brilliant lesson, but the assessor might have been looking for something completely different. So we have to be mindful of what our audience is. I'm an inquiry-based lead and I'm inquiry-based practitioner. I've over 100 publications, so I'm told, and they are all based around inquiry-based learning. All my lessons that I teach are inquiry-based, and all the CPD sessions that I deliver are all focused, or inquiry-based is always at the centre. Now, at the heart of inquiry-based learning, through my experience, is a question. So we might be asking questions like the one in the picture. So if we looked at those pictures and we said to the students, is this reaction reversible? Or we could say, is this reaction irreversible then? How do we know? We're constantly asking questions. We're constantly developing questions and designing questions. It's at the heart of learning and the heart of teaching. And so we're very good and we're very experienced at it. Do we plan these questions? Now, if it's at the heart of learning and it's at the heart of teaching, then why don't we plan these questions? We should be planning these questions. We should be considering what questions we will ask, when we will ask them, who will we ask them to, who will we decide, who in the room will we point that question at, why will we ask that student that question? What's the purpose of it? What answer are we expecting? What are we looking for? Why have we asked the question? So, what answer are we expecting and anticipating? What will we do if the answer is not what we were looking for? What will we do if the answer to the question that we're given isn't what we were expecting? It's totally different, or it's slightly different. And what will we do with that? What will we do with that situation? Now, in order to address this successfully in every lesson, we would plan these questions. But I always say to teachers, do you plan your questions? And teachers are very good. They're well-trained people. They know what they should say, what the answer to that question should be. And that should be, yes, I do plan my questions. And so I always say, show me. And to date, I have never really, other than a trainee teacher, seen questions planned for individual lessons. Because as teachers, we're very experienced and we don't do that. We don't need to do that. And I'm not talking about all the questions. Where's your homework? Where have you been? Why is that on fire? I'm not talking about that. I'm talking about the backbone questions that we hang the lesson on. And these should be planned, and they should be well planned and thought through. I call this agenda building. Agenda building is a technique that's been used over the years that teachers use. The reason I use it is because in the last few schools that I taught in, there wasn't an official lesson plan that had to be designed. So the teacher was quite free, really, to design their own lessons using whatever format that they wanted to. And I found agenda building really useful because I found that I taught maybe the same lesson 2 or 3 times in a week because it was a big school. So you had lots of different classes in the same year group studying to the same exam, the same qualification. But I had to differentiate quite substantially because there was a massive range in this massive school of ability and capability. And so I found agenda building really useful because the graphic, the images of a lesson for me. So the objective was at the centre, The questions would be written off like a mind map, activities written off, all the different kinds of sorry about that. That was the other line going there. All different kinds of information that was useful for the lesson, including what kind of stimulus you would use, and also the questions that you would ask. So agenda building could start with something like this fascinating fact: if your body became too hot, the capillaries in the skin widen. You can read that for yourself, you don't need me to read that. But how could you link that to the content of a lesson? And it could be that you're doing about keeping the body cool, homeostasis. How would you cool the body down? How would sweat help that? How would the capillaries work? It could be linked to a lesson on circulation, where you could be introducing capillaries as one of the blood vessels that carry blood to the surface of the skin. If it's on the surface of the skin, then what properties would that vessel need to have? Would it be like an artery that's a thick, muscular blood vessel, or would it be something that's really thin and could travel across the surface of the skin? And so that might be used in a lesson. If we're planning to deliver a practical, or we want the students to engage in a practical or a practical investigation or activity, why are we doing that? Often when I'm observing lessons, I'll be faced with a fantastic practical that the students are all engaged in, they're enjoying, and that's good. That's good because they're engaged and they're interested in science, and that's always good. But then when I look back through the books and I see what they did last lesson or last week, and I ask the students, what have you been doing in science? What have you learned about? Sometimes I look at the practical and I think, why are you doing that? Why are you doing that practical? And unfortunately, it's often for the sake of the practical, to impress me, to impress the observer, rather than to deliver the content of a lesson. Now, I've been involved in developing curriculum quite substantially over the last couple of years, really. And I believe strongly that the practical aspect and the activity side of science, the investigative side of science, should be blended. It should be blended with the content. It shouldn't be in addition to the content. It shouldn't be a hang on to the content. It should be part of the delivery of that content. And so practical should never be done for the sake of practical. So when you're planning this lesson, think about, why am I doing that activity? Why am I doing that practical? What's the point of it? And how much does it link into the objective of the lesson? Then you need to think about, have the students got sufficient background knowledge? Do they understand? Do they understand enough so that they can actually engage with the content of the lesson? How will you get the students involved in the lesson? How will you feed that curiosity from the start? And I use stimulus to do that. I was talking earlier about a stimulus early on when I was really interested in inquiry-based learning. I decided one day that I would really focus on stimuli. I would really try to make every lesson have some form of stimulus which would engage the students from the second they walked into the lesson. And the lesson that I happened to be planning was one that I'm not very keen on, which would have been a biology lesson. Biology, yeah, it's okay, but it's not really my path. Often I have to work in biology, um, circulation. Circulation sometimes found really difficult for some children because they know it's there and they know it exists. It's actually a lot more complicated than they think it is. So I came up with a glass bowl, a glass dish, so it could be seen all the way through, top, sides, bottom. And I filled it with blood, which was really poster pen and ink. I don't know if you've ever used poster pen and ink. If you have, you'll know that it's messy. Yes, you can make it look like nice, thick blood, the right consistency and the right shade. But it's not the easiest material to work with. And then I cut a heart out of jelly. So I made a jelly mold to look like the shape of the heart, and I cut into it so it looked like a heart. And as I dropped it into the bowl, I could hear the students racing down the corridor, and that shocked me a little bit. And I remember thinking, why are my students racing down the corridor? What's actually happened? Why are they so energetic? Oh dear, this is not going to be a great lesson. And I dropped the dish. The blood went everywhere, in my face, my hair, down my arms, my clothing, my legs. I grabbed tissue from the side. It was actually one of those fantastic paper towels that we have in school that often just moves things around rather than absorbs it. And I ended up with splatters of bright red that I'd tried to rub off, that had actually rubbed into my skin as the children walked in. I remember looking and thinking, where's the heart gone? And the students were saying, oh my gosh, miss, you've killed someone. You've murdered someone. There's blood everywhere. You're covered in blood. Oh my gosh, there's a heart on the floor. Is the heart still bleeding? Because the heart was made from jelly, it did look from the vibrations on the wooden floor like it was still moving. Oh my gosh, the heart's still beating. No, it can't be beating, because a heart wouldn't beat if it wasn't in a body. Would it bleed if it was would it beat if it was in a body? And I said, well, yes, it would, because it needs an electrical stimulus. And while ever it's got that electrical stimulus, it would beat. Bingo, straight into the lesson. Okay, they thought I was some kind of a mass murderer. But suddenly they were engaged and they were interested in the heart and the circulatory system. So for a stimulus, you consider what are the possibilities. You can't make a bowl of blood every lesson. I get that. We're busy people. We're very busy people. We can share stimuli though. We could make some blood and share it with another class. We could play some music. We could show a video clip. We could bring another model from another class that older students had made, studying a similar aspect of the curriculum. We could ask older students to come in. We could ask people to come into the classroom, like a surgeon or an ophthalmist. We could dissect an eye, or we could dissect a real lamb's heart or a sheep's heart, whatever we could get safely. And so the stimuli are really, really engaging and important in this kind of a lesson. But the world's your oyster. You could really, really explore and engage and, experiment with this and find out what your students like. Some students might not like a heart floating across the floor, others will. You know your students, and so you can come up with some fantastic, fantastic stimulus. Good afternoon, everyone. Getting lots of people saying good afternoon. I really like that. That's nice and interactive. We're almost together. So good afternoon to you all and welcome, welcome. So a question then. Lead into the lesson with a can-do question. To most people, that would be a closed question. Why do I call it a can-do question? Because we carried out some research and we were in a very, very large school. It wasn't my school, and we stood in reception, and as all the students came walking in, we asked them what subject they'd got first. Where are you going to? What will you be learning about? And all the students who said science I was particularly interested in, so I would say, do you like science? Are you good at science? Do you enjoy science? And I was really disappointed that most of the students said no. No, I don't like science. I don't enjoy science, and I don't really want to go to science, but I'm going. And compared to other subjects like PE or cooking or any of the hands-on engaging subjects, I was really disappointed because their opinions were very different. So where I had time and there was some of the students seemed to want to engage, I asked them, why? Why don't you like science? I love science. Why don't you like it? And they said, the most common answer was, it's too difficult. It's too difficult. It's really hard. I can't do it. How long have you been studying science? Well, just a couple of weeks, couple of months, a year. So you've not been studying it very long then, have you? How come you know that you don't like it so much? And it's really odd and sad to say that their responses was, because my mum said she didn't like it, my brother, my sister, my cousin, my auntie, my friend. It's difficult. It's really, really hard. And someone's just said, but all these hands-on engaging subjects use science. We know that. We know that. But do students know that? And the answer to that is most likely no, because some of these subjects don't actually use the science. Why? There aren't many science specialists out in primary schools. There aren't many science specialists who are really confident to be able to integrate science into other subject areas. That's the main reason. But using a can-do question, suddenly you're faced with students who think that it's a difficult subject and they can't do it. Now, you imagine if you were faced with a challenge or a problem in your life now, and you thought it was an area of your life that you were not very good at, you couldn't do. It's very difficult, it's very hard. Recently, I was asked to learn computer science, programming, computer programming for older students. And I thought, I can't do that. That's really difficult. That's really impossible. And automatically, you're making the learning twice as difficult because you're telling yourself all the time, you can't do it. I can't do this. I'm going to fail. I'm not very good at this. Using a can do question or a closed question, please bear in mind a closed question is not yes or no. Lots of people think it's just a yes or a no answer. It's not, and I'm sure you know this, and apologies if you do. I'm just using this as a reminder. It's one with limited answers. So the chances of getting it right are massive. So by asking a question, look at that picture. What can you see? What's this process called? Lots of teachers have said to me, well, it's called burning. It says burning on the picture. Yes, it does. But for a student to use those skills, there's a picture of some paper being burned. It says burning. It must be burning. Burning. Correct. Well done. Can you see the difference? We started thinking, I can't do this. I can't do this. It's too difficult. I'm not very good at this. I'm going to be in trouble. I can't do this. Someone's just said, like driving lessons. Yeah, absolutely that. And you put so many barriers in your way because you feel, I can't do this. This is out of my comfort zone. This is out of my specialism. This is not my skill sector. But by doing this can do question, like, you are good at driving, your driving instructor tells you. You did that really well. Well done. Forgets that you've done lots of other things not particularly well, but it makes you feel different. And the can do question makes students feel different. She just said, I did really well then. My teacher just said I got that right. That's the first time I've had to go answering a question in a long time. And I got it right. I can actually do this. Can you see the difference? We're going in with a completely different approach. And for problem solving, that's got to be the case. Students have to feel, yes, I can do this. When we're thinking of problem solving activities and investigations, we need to make sure that they will be successful. Otherwise, they'll have the complete opposite impact on their learning and their confidence levels. So we need to think about some things before we actually put that investigation or that activity before them. Because remember, we want them to engage in it independently. We want them to take responsibility for their own learning journey. And in order to do that, we need to make sure that they can do it effectively and safely. What do they need to know before? So if you're thinking up an investigation, think about what information do they need? What prior knowledge and understanding must they have in order to engage in this fully? How can we find a solution? How can they, what am I looking for? What expectations have I got? What are they likely to come up with? What do you think they will be thinking? Can they actually make a prediction about this? Have they got enough knowledge and confidence and skill set to be able to start to make a prediction? Because in science, regardless of the age group, we want them to begin with a question, and we want them to predict what they think based on their understanding and knowledge a sound prediction will be. And then we want them to be able to come up with a prediction that can be tested. So how can they test this? I'm going through this lesson that would be days worth of learning. You might not decide that you want to start by thinking about the variables and the investigation, because you might want them to focus on making predictions and testing predictions. And so you might give some of this to them. And at different points, you might focus on different aspects of science methodology. So if we were looking at a fair test, we would be really interested in what the variables are. Now, someone said to me 2 days ago, students in primary school don't understand what a fair test is. Excuse me, they do. If you've got two students, I had two sons 18 months apart, and when they were little, they knew what a fair test was. Not because I was a scientist, but because they knew what an unfair situation was. If I gave one of my children a chocolate bar and I gave the other one nothing, they would say, but that's not fair. Children understand from a very early age what being fair is and what a fair test is. We could say, what are the variables? The variables are the factors, the things that are involved in your investigation. The independent variable begins with I. I begins also with I. The independent variable is what I am in control of. I will change the temperature. I will change the container. I will change the type of fuel that I'm burning. I will change the food that I'm burning to see how much energy is generated when it's burnt. The dependent variable is what I measure. I am changing the kind of food that I am burning, and I am measuring the change in temperature of the water when I hold the food sample on fire underneath it. What are the control variables? Someone again in the same conversation 2 days ago said, you can't really control variables in a primary investigation. It's not complicated enough. Well, it is, because I was told earlier on this afternoon that in the Caribbean it was 23 degrees. Okay, so that's a few hours ago, where you are now. I was most upset and jealous and envious because it's 3 degrees here. Well, I don't know what it is now. It's probably less than that, because this was a few hours ago when I checked it. We're still in the middle of a storm, and it's not stopped raining for 2 days. And it's freezing. It's cold. It was snowing a couple of days ago. We had lots and lots of snow and ice. And so if I said to you now, put an ice cube on your windowsill and time how long it says to melt, and I'll put one on my windowsill and I'll time how long it takes to melt, and then we can fill this table of results in it. You can be test 1 and I'll be test 2. I'm guessing that my time would be minutes and your time would be seconds. Oh dear. Shall we just keep repeating that? You put another ice cube on your windowsill. I put another ice cube on my windowsill. No, we're not controlling a particularly important variable, are we? The ambient temperature. The temperature in the room will impact on the dependent variable, and it'll be nothing to do with the independent variable. It's just the fact that my room is much, much colder than your room. And so we need to control that. So if I said to you, take the temperature of the room and I'll take the temperature of the room, and I'll put the heating on and you put the air conditioning on, and we'll get it so the temperature's room temperature about 19 degrees or something like that. And then we'll put an ice cube on our windowsill, and then we'll time, and then we can use the same results. And we could do that all over the world. Every single one of you on this webinar now could do that, and we could pool resources, and that result would be really reliable, and we would be confident with it because we've all carried out the same investigation that's repeatable because it's controlled. Recording results is a question that lots of people ask me, even up to secondary level, not just primary level. Drawing a results table can be very time consuming. Now, It's important that students understand the table of results. It's important that they understand that in the first column it's always the independent variable, apart from some cooling curve investigations and things like that from later on in school, where we do them the opposite way around, just so that we can see the curve nicely on a plotted graph. We'll not get into that, but just save you telling me that, you brilliant scientists out there. In the second, third, fourth columns are always the results, the dependent variable, what you're measuring. There should also always be the unit of measurement, always. This is really important because there was a famous collaboration of investigations where two universities were figuring out how much fuel it would take for a rocket of a set mass, set area, set control variables, how much fuel would it take for them to actually get into orbit. And they came up with completely different results, and it was a bit startling, really, until we realised that one had worked it out in kilometres and one had worked it out in miles. So in the table of results, it's always really important that we actually put the unit of measurement, and that's standard. That's accepted as standard form in science. But do we waste time drawing tables of results, I'm asked? Yes, we do. And unfortunately, we need to spend more time in early years and in primary school. Why? Because they need to understand the purpose and the layout and the rules of using a table of results, because then later on they can read and use and analyze the data that's in a table of results confidently. Because let's be honest, when these students are older and they're working in a science background, they won't draw their own table of results, and they will not plot their own graph. These will be generated through computer technology. They won't be doing things like that in their workplace or in further education even. So do they need to be able to draw a table of results accurately? Not really, but they do need to be able to use them and understand them accurately. So if that means investing time, they have to. When they've designed their investigation and they've come up with the variables and the method, and they know how they're going to work it out, what they're going to do, how they're going to test it, they'll then be wanting to tell us what equipment they need. You need to look closely at that equipment. The investigation that's on screen now is a really simple one. It uses a sheet of paper, a metal plate, some weighing scales, or a top pan and balance. They should be able to use that quite accurately, but do they? Can they use the weighing scales? Can they measure accurately? That's for you to find out. Can they use it safely? Because if they can't, if the answer to these questions is no, then you need to think about, is this investigation right for them? Do they need to use a simpler investigation that will train them to use this equipment and will train them to use it safely? Can you trust your class to set fire to a piece of paper on a metal plate? Probably not. Do they need to measure and weigh using the scales the paper on the metal plate? And then can you go around and set fire to it and make sure it's extinguished safely and correctly? Can you make sure that everyone else in the room is safe? Do they know to stand back? We're going to set fire to this piece of paper now. Please stand back. Now we're doing this one. Stand back. We've got a fire extinguisher. We've got a fire blanket. We've got some water that we can extinguish the flames safely and easily. There's a ventilated, well ventilated room. So when we're burning the paper and we get that thick carbony smoke, we can make sure it leaves the room quite safely. Do we know everyone in the room? Have you checked to make sure that there aren't students with breathing difficulties, for example? Do we need to let students that have got some form of breathing difficulties, is it safe for them to stand next to a window when we do this? Or do they need to stand outside the window and look in? Can they use it safely? How long will it take? Who will they work with? How will you organise the groups? Will you organise them so there's a higher achiever. I don't like that expression, but there's no alternative that makes sense to all of us. High achievers mixed with low achievers so they can support each other and work together independently, as much without the support of the teacher as possible. Do you have higher retainers together so that you can challenge them sufficiently and well, and have lower abilities together so that you can support them? Do you need someone else to come in and support you with these children so that they can all engage in this activity? How long will it take? Have you got time to do it? Some of these purchased lesson plans I look at and it says, this will take 40 minutes. And I look at it and think, no, that won't. That will take about an hour to get through all that. So think about that. How much time have you got? How much time can you invest in this? Does it really take that amount of time? Test it. What will they measure? What will they observe? Remember, observations do include measurements. They're not just, it's blue, it's changed colour. It's also, how long did it take to change colour? We measure as well. How will they record these results? Probably in a table of results. And what will they do with the results? Now that's the important bit. We want them to engage with the results, to analyse them, to really, really think about them. Get their students to use some of these engaging talking points. These are in some of the mission science resources, by the way, but I'm sure you get the gist of it if you're not using them, that you can encourage students to discuss and talk together, because they'll learn more from each other than they ever will us, because what do we know? But they're more confident if they're talking together. Has the weight changed? Why might this have happened? Did you see anything escape into the atmosphere? So if they measure the weight of the paper at the start and the weight at the end and there's change, why might there have been a change? What could have left that system? What does burning need? Well, it needs an ignition, which will be you setting fire to it, a lighter, a match, safety lighter, safety flame. The fuel, what will the fuel be? Well, it's the paper. What else does it need? It needs oxygen. So does that mean that it will increase in mass or will it decrease? That's for them to work out. These are why we've got these questions, to lead on to challenge, to make them think outside the box and beyond that lesson plan. So could you give them something to encourage them to recognise and identify patterns and trends in data? I always think this sentence, this model of a sentence, this writing frame works for nearly all investigations that we ever carry out in education and beyond. As the something increases, the something else might decrease or increase. As the amount of carbon dioxide increases in the atmosphere, the temperature also increases. So we can use this writing template or this model to get them to look at the results and think, oh, I see what you mean by a pattern or a trend. As that goes up, that goes down. As that goes down, that goes up. And they can begin to write that into simple sentences. Do the results report or support or refute? Somebody told me again in the same session the other day that students of this age don't know what refute means. No, they don't. They don't know what a lot of words in science means. Lots of people don't know what words in science means. Where else are they going to learn it but from you? We learn as human beings by copying, by observing, and by listening. Where else are they going to use the word refute? Probably nowhere. But if you keep using that word, refute, no, it doesn't support my prediction. It refutes it. It refutes my prediction. They will learn it and they'll be able to use it confidently and competently because they've heard it so many times. It's almost like parrot fashion. And then why? Why does it refute it? Well, because I thought that the mass, the weight of the paper would decrease after it had been burnt. And so these results don't actually show that. Why is this? Is your prediction wrong or are your results wrong? And if your results are wrong or not what you expected, because in science nothing goes wrong. If it did, we wouldn't have a Buckminster Fullerene, for example. Things don't go wrong, but they don't always go the way that our predictions think, the way that we think something will happen. So what can we do about that? What do we do if things don't go the way that we expect? Well, we develop our growth mindset and we go, yes, it didn't go the right way. It didn't go the way that I thought it would go. But I was such an amazing scientist that I know exactly what to do about that because I've got the tools and the resources to help me get out of this. And I'm going to repeat the investigation. I'm confident that my method's right, so I'm going to try it again and see if I get the same result. And if I do, I'm going to compare it to someone else and see if someone else has got the same results or similar results to me. What does this develop? It develops resilience. I will keep going. I will find a solution to this problem. I can do this because I have got the right tools. It develops patience. I've done this experiment 4 times. My friend over there has done it 7 times, and we still keep getting the same result. But it's not what I expected. And I'm still confident that my setup and my investigation is right. So it develops patience. I am going to ask other people what they've done and what results they've got. What's that develop? Collaboration, and also communication, because you'll feel so amazing when you hear a student go to another group and say, my results are continuously refuting my prediction. Do your results refute or support your prediction? How good will you feel when you hear students using language like that? And by getting things not the way they expected, they've got opportunities to practice this. So what shall they do next? Is it repeatable? Can they share the results? Did they all get the same result? The result they didn't expect to get? Is it the fault of the method? These are the questions that eventually, through training and practice, we want our students to be asking. We want them to come to us and say, Miss, Sir, this investigation that you've told us to do just does not work. I think it would be better if. How good would that feel? Research is one of those skills that is used a lot now in science, and particularly over the last year where we've had these difficult times, we've had to become very creative and we've had to develop lessons that are well out of our comfort zone that we were never trained for. So we've had to develop lots of opportunities for blended learning where students can do some work remotely, where they can work with you when they can, but they're still learning. And research is one of these key areas. I've included these research tasks because I think now and for the future of education, research will become bigger and bigger and bigger. And as our students move out into the workplace, into the next provider in their educational journey, research will become more and more important and significant. So in these questions, students are asked out to find the temperature of the water that the water has to be in order for the liquid water to change state into water vapor. They could actually find that through asking other people or perhaps in a book. Certainly in the books that they've got in science, that would be in there. Or they could it could become a research task where they need other resources. For example, it could be an ICT task where they're using the internet. This is really important again because students need to be competent and confident and need to be able to use the internet safely and accurately. They need to be able to recognise that if a piece of information on the internet is not reliable, they don't use it. And they need to be confident enough to consider, I can't do that. That's not right. That doesn't look right. That doesn't agree with what I think. And they start to question rather than just taking it at face value. The real world science that we can see on this page also, if we can introduce these to children, it makes them realise that science is not this difficult subject that we just have to know. It's actually a method of finding answers and solutions to problems and the bigger picture, and that scientists are working away using the skills that they're developing now. And they are scientists because a scientist is someone who practices science, and they are practicing science. If you can find people that are from their region, their area, their country, that also shows these people have studied what I'm studying now, and they've become successful scientists and are helping people like me in my country. So now we've gone full circle. You started planning your lesson, considering all the different aspects of it. Have we got time? Do they understand this? Are they skilled enough to involve themselves and engage fully in this investigation? And now we're coming back to, so what do I do with that information? What do we keep the same? What do we need to change? What shall I change in that investigation? Do I need any help? Do I need to use different equipment? So we're starting to go full circle and we're using that information. So do we need to repeat investigations? Do we really need to do that? In order to get reliable results, we need a big resource, a big source of in results. But do they need to repeat it? Well, as we've said, if the investigation is repeatable, other people can repeat it, and you can use the results and pull the results together and confidently use them if they've all followed the repeatable investigation. Will they learn much from repeating? Well, we do want them to understand that that's what scientists do. If you were using a new vaccine and it had only been tested on one person, but the result was good, would you rely on that? No. You'd want it to be tested with lots and lots and lots of people before you were confident that it was a good idea and safe to use. And we want children to understand this from an early age. Scientists repeat things to make sure the result's right, because it doesn't always go to plan, and that's absolutely fine. But in order to be reliable and so we can be confident with the result, we need to be confident enough to repeat the investigation. Have they taken responsibility for their own learning? So at the end of the lesson, when we're reflecting on what's happening and what's happened in a lesson, we said at the beginning when we started planning this lesson, this imaginary lesson that would take days to do, because you are going to focus on just particular aspects that your students need to focus on. We would reflect. Reflection is valuable and key in education, and it's something that busy teachers rarely do. But when we're training, we're almost encouraged to review and reflect on our lessons, because that's how we make progress. We want the children to review and reflect on the lessons, and we should be doing it also. Did they write their own prediction, or did you give them predictions? Next time, would they be able to write the prediction? Are they trained enough now? Have they got the skills to do it? Did they design their own investigation, or did you tell them what to do, and did you give them step-by-step instructions? Next time, can you take some of that away and allow them to do a little bit more and a little bit more? Did they work independently to find the solution? Were you constantly telling them, stop in the lesson, try this, do this? Did they analyse their own data? Did they collect their own data? And did they analyse their own data? Can you do more next time? As you've observed them in that lesson, did they surprise you in what they could and couldn't do working as a team? Did they suggest? Did they make suggestions? I think next time we should do it this way or that way. Let's miss out that step. What do the children think? How do you know? How do you know if they were engaged and motivated? How do you know if they took responsibility for their own learning? And how do you know what skills they learn? Well, I'd like to think you know that they've been motivated and curious, because in my lessons, I know if they're motivated and curious because of the noise volume. Miss, look at this. Sir, look at that. James, watch this. How did you know if they took responsibility? Because you know what? They just got on with it. And even if it didn't go to plan, they got on with it and they did it. What skills did they learn? Well, if they got on and did it, they learned to be responsible. They learned to be motivated. They learned to have the confidence to be able to do it. How do you know they've made progress? How do you know in that lesson There are lots of opportunities in the mission science resources, and I'm sure that you can see how you could use them in your lessons and you could develop them yourself. The test yourselves are at the end of every single learning objective, at the end of every lesson. And you can use these just to get the students to tell you an answer. Or you might want them to write an answer. You might want them to take it home and do it at home in a different environment. The talking points move around, circulate, listen to what they're saying. Because that's live marking. So you hear, why do you sweat? Why is sweating important? My mum says that sweating's important because it makes you smell and it scares off dangerous animals. You could address that straight away, hands on, live marking, which we now know researchers are telling us is powerful marking. It's instant feedback. Or you could use the Check Your Learning, which is more of a formal assessment that can be used at the end of a full unit, or it can be used, you could ask questions at different times throughout that unit when you think that it would support learning. Do you ask students, are all assessments, should they all be in silence? Should students always work on these assessment opportunities in silence and respond to them independently in a written format? Or is the value in students being asked to work with another student comfortably and relaxed? Which one of the following is a physical change? Would that be okay to ask them to work with a partner, to go through the answers and think, I think it's that, we think it's that? They could then share that response with you. We think it's this because. Or do they work together, work through the question, then go away and answer it more formally? Does it actually matter? It might be that they were going to actually give you the wrong answer. But by working with someone, chatting about it, talking about it, working through the question and forming an answer, they've actually learned. So does it matter? Does it matter how they know this? Or is it more important that they know it? That's for you and your situation that you're in, but it's definitely worth considering. The whole point is so that students learn information and learn skills. It doesn't really matter how they learn those skills. It matters that they learn those skills. And so assessment really should be used in different ways. I'll admit I'm not a lover of assessment. But how do we know that students are making progress unless we assess? So informally, it can be listening to conversations, listen to discussions, listen to their ideas, and attack them straight away if they're not right or they need intervention. Test them in different ways, discussions, test them in ways where they are starting to get ready and prepared for formal assessments by answering questions like this. But be aware that we're asking these questions for a reason, and that's to find out how much they understand, not how well they can do at answering questions. But I understand as they're getting nearer and nearer to formal assessments, they need to be confident and they need to understand formal assessments. So when they've had these assessments and they've taken them and they've given you their answers and you're looking at them and you're assessing them, what do you do with the outcome? What do the students do with the outcome? What do you do? And what do parents, carers, investors do? What we need to do is not wait too long to give feedback. All of the research tells us that as soon as we get feedback, we look at the mark. I got 94%, I got 12%, I got 2%, I got an A, I got an E, I got an F, I only got 5 out of 15, I got 1 out of 25. All of us. I've worked with lots and lots and lots of educated, experienced people. And when I say, how did it go? How did you do? I only got 25%. Yeah, but what did you get right then? I don't know. What do you need more support with? I don't know. I just got 25%. I'm so disappointed. And we all do that. And the research tells us we do that. Is that constructive? No. Will that help us? Not at all. Will that help us to make progress and understand? No. It will deflate us. Some students also tell me, I got that result, but I can't remember what it was for. So it's got to be really as quick as possible, almost instantaneous feedback. And I know we're all busy, but really do an assessment for students, unless they get quick feedback, there isn't any point for the student. It's just stressful. So what do the students do? What they need to do is, if you've got time to give them an assessment, a test, give them time to look at it, review it, and to analyse it. To reflect, did I work to the best of my ability on that assessment? No. Could I have done better? Yes. What did I get wrong? What do I need to learn more of? Do I need my teacher to help me with this? Do I need to work on this more? Did I understand the question? What do you do? Oh my gosh, they've all got it wrong. They've all got question 3 wrong. I need to reteach that in a different way. They clearly didn't understand that. So I need to do that again. But I need to do it differently because it didn't work the first time. So it won't work the second time. What do the parents do? Well, it depends on how we feed that information to them. If you say your child got 3%, what does that do? If the student goes home and said, I didn't do very well in that assessment, what does that do? That's all negative. What we need to do is be saying, okay, so we did really well in this, but we need to also look at this, this, and this. We've got lots of time, but we do need to work on it more. We use it. We plan more. We don't take it personal. We don't get upset. We just take it on board and we do it again. But we do it differently. We prepare. We be prepared for students to need more. We're organised, so we don't leave it until the last minute. We're confident we can do this. If this didn't work, but this will work, we can do it differently. And we become the best that we possibly can be. And our students become the best that they can be, because that's our job. Our job is to give them the most information, the most relevant information, in the best way that we can possibly do that. And you did it. There you go. You survived. That is the end of this session. And you survived it, and you did it, and you will do it, and you'll continue to do it. You know why? Because we're in it for the right reasons. We want the students to become the best that they can possibly be. And sharing good practice and sharing ideas in sessions like this is the best thing that we can do as educators. I've thoroughly enjoyed working with you all today. I've thoroughly enjoyed your feedback. I am absolutely loving your positive praise, because I'm sat here in the front of a computer on my own doing my best. But if my best's not good enough, only you can let me know. So thank you so much for these wonderful comments that you're writing at the moment. I really do appreciate that. And so that comes to the end. If you've got any queries or questions, please, 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 I will try and answer them now before we go. If not, you can get us here through these various different methods and addresses and things. And that's the best that I can do for you today. So I'll hand you back over to Raina, who I'm sure will have more information for you. Thank you so much. I thoroughly enjoyed that. So thank you.
Perfect. Thank you so much, Debbie, as always. And I can tell from the feedback that our attendees really enjoyed the session. So thank you, as always. Debbie does a fantastic job, and it's always so detailed and informative, and the ideas are always so creative. So thank you so much to Debbie for her webinar. We do actually have more webinars coming up with Debbie in the coming weeks. So please do check out our website for more information about our upcoming webinars. If you have any further questions, do email us. The PowerPoint and the YouTube link for the webinar will be available hopefully within the next 2 weeks by email, but your CPD certificate will be automatically available as soon as the webinar finishes. So thank you again to Debbie. Thank you to the attendees, and we look forward to seeing you in an upcoming session soon. Take care. Thank you.
Bye. Thank you.